Welcome to Science Academy, and today I want to talk about X-rays in 5 minutes. So let's start with the classification of X-rays into the electromagnetic spectrum. So you probably all know the electromagnetic radiation from light, right? What you can see is just roughly from 400 to 700, maybe 750 nanometers, right? This is just this single part in the whole electromagnetic spectrum. And if you go to the higher energies, we come from the ultraviolet into the X-ray spectrum. Of course, if you go to higher energies, the wavelength gets shorter, the frequency gets higher. So we have frequencies like 10 to the 18 hertz, which corresponds to roughly 1 nanometer of wavelength and would be like around a few kilo electron volts in energy. Or if you better know the joule as a unit of energy, it would be like 10 to the minus 16 joule or something, right? So this is basically how where the X-ray sits in the electromagnetic spectrum, but where does it come from, right? How can we generate X-rays? And it's usually best explained with looking at an X-ray tube. So this is just a simple model of a tube. We have like a small vacuum chamber, so there's no air inside. And then we have a cathode and an anode. And the cathode is heated so that the electrons in the cathode can easily be pulled out. And then we have an accelerating voltage between the cathode and anode so that the electrons are accelerated towards the anode and then smash with a high energy, smash into the anode, and so are quickly decelerated, and then because of that produces X-rays that you can measure outside them, right? So the question is basically what process in the anode material happens so that X-rays are generated with that. So there are two main processes that happen in the anode when such a high energy, so high speed photon hits the atoms of the anode. And the first I want to talk about is the so-called characteristic X-ray emission. Characteristic in that sense for the anode material. So we have a high energetic electron, and we knock an electron out of the inner shell, called the K shell, of an atom of the anode material. So we have this high-speed electron hitting the anode, and we just kick an inner electron out. And of course, now there's a gap, there's a hole, an energy hole, right? And an outer electron, for example, from the M shell or from the L shell, will fall down into the better energy state, lower energy state, and fill up this hole. And the difference in energy between these two shells has to be released. And this is exactly the characteristic X-ray radiation we see in the end. You can see that if you look at the energies here on the right, so those peaks are called K because we hit an electron in the K shell, and depending from where another electron fills up the hole, so if it falls from the next shell, which would be the L shell, it's called K alpha. If it falls from the L shell, it would be called K beta, and so on. Of course, K beta, for example, has more energy. You see it on the right as K alpha, but we still would expect K alpha to be more likely, because it's more likely that it just the gap, the hole is just filled up with an electron falling from the next shell, right? So this would lead to a discrete energy spectrum with peaks, discrete energy peaks at this K alpha, K beta, K gamma, and so on levels, right? Sharp peaks. And then there's another process called Bremsstrahlung. It's actually a German word, and it just stands for decelerating radiation. So this time, our high-speed electron hitting the anode doesn't really hit an atom or hit an electron, but it's just decelerated by the electric field of an core, of an electron core, right? So of an atomic nuclei. So we have this interaction between the electron, high energetic electron, and the nuclei. It goes into kind of an orbit, like you would expect with planets, for example, that orbit the sun, right? And if a charged particle is decelerated, it always has to radiate. So it loses kinetic energy, and this energy has to go somewhere. And in this case, this is the X-ray radiation that is generated here, right? But this is just a continuous process, right? Could be closer to the atom, it could be far away from the atom. So you would expect like a smoothly, distribution of energy X-ray photons here, right? And that's exactly what we see. And if we look at the outcome of both of the processes, we will end up with such kind of spectrum. So here we don't have the energy on the x-axis, but we have the wavelengths. So on the left we have the higher energies, and to the right the energy is going down, right? And we see the two peaks, K alpha, K beta. We also note that K beta has a higher energy as we expect, because it's on the left, right? On the x-axis is the energy, left shorter wavelength, higher energy. But we also see, and on the y-axis we have the intensity, which in this case just means how often does it happen. So we also see K alpha is more probable than K beta, right? So like we expect, we also see the so-called Bremsstrahlung spectrum here. So just a continuous radiation of Bremsstrahlung overlapped with the characteristic spectrum. You can generate such X-ray spectrums by using something called X-ray crystallography. But just that you can read it up if you want to. I don't want to talk about it right now. So that's it for now. I hope you liked it, and you should leave a comment and follow it if you want to see more of those.